we're going to do a couple problems from chapter 39. The first problem we want to do is problem 4. And the problem says an electron trapped in a one-dimensional infinite potential world, 250 picometers wide, is in its ground state. How much energy must it absorb if it's to jump up to the state with n equals 4? So in other words, we have an electron that's trapped in the infinite potential world, and initial state is a ground state. So initial state, if that's ground state, your Ni is 1. It wants to jump up to the state with n equal to 4. So the final state is equal to 4. So that's your fifth, let's see, that's your third excited state. Okay, so and the length, the wheel width is 250 picometers. So you're asked to find how much energy is required for the electron to jump from its ground state to the let's say you have this energy level, and this is n equal to 1, that's your ground state. Then you have the n equal to 2, first excited state, n equal to 3, second excited state, and n equal to 4. That's your third excited state. Okay, so ground state, third excited state. How much energy is required for the electron initially at n equal to 1 jump up to n equal to 4? So the equation for an electron, the equations for the electron that's trapped in infinite potential world is this. So your En, this is your En is h squared over a times the mass of the electron times the well width square, and then times the quantum numbers square. So in order to find the change in energy, we have delta E that is equal to, when the electron is in the third excited state, minus the energy when it's in the ground state. So when you do this, just replace your m by whatever number that you're given. So you have your h. Now the h, again, we're going to use the SI unit. So your h here is 6.63 times 10 to the negative 34, and that you square it, that's your h squared, and then you have a times the mass of the electron, which is 9.11 times 10 to the negative 31, and then times the well width, which is 250. It's picometers, and pico is 10 to the 12. So you convert that to SI units, and you square it. Now, because if you look at the equation, you'll know that the E4 and E1, they all have the same parameters here. So you can you can put the outside parentheses, and then within the parentheses you have your 4 square minus 1 square. So after you punch in the calculator all these numbers, the change in energy is 1.447 times 10 to the negative 17 joules. Now, if you want to convert it to EV, then it's everything divided by 1.6 times 10 to the negative 19. That converts the joules to EV, and you'll get 90.47 EV. So that's the amount of energy that is required for the electron to change its state from the ground state to the third excited state. So again, I will be happy if you just have everything in SI units, okay? And this is if you after you calculate the energy in in joules, uh you can use that number divided by 1.6 times to the negative 19. That will give you the energy in EV. Okay, so that's problem 4. Now we'll want to do another one that deal with the electron trapped in an infinite potential well. So again, this is problem. Let's see, this is problem 12. So problem 12, we have an electron is trapped in a one-dimensional infinite potential well of width 250 picometers, and it is in this ground stage. For all the longest and second longest and the third longest wavelength of light that can excite the electron from the ground state via a single photon absorption. In other words, you have this is the energy level diagram. You have energy of an electron, and the electron initially is in its ground state. You want to find the longest wavelength, the second longest, and the third longest. So as we mentioned, the change energy and the wavelength are related to each other, and they are inversely proportional to each other. The larger, if you let's see. So if you want your lambda to be large or the largest, then the change of energy has to be the smallest. So that's a guideline in order to find what is the change of state. So in this case, your P here is 250 PM, and and the energy for for the electron trapped in the infinite potential well is h squared over a times m l squared and then n squared. So in order for the problem A, the longest wavelength. If you want to have a largest wavelength, which means that the change in energy has to be the smallest, so it can be accomplished when it changes from 1 to 2, from the ground state to the first excited state. This when n goes from 1 to n goes equals 2. That gives you the smallest, your delta E is smallest, which means that your lambda will be the largest. So having said that, we can find out we can first of all find out the change of energy. So your change of energy would be E2 minus E1. That's the energy difference. So we just plug in the numbers. So again, everything has to be SI units. So and the change of energy you can calculate using h squared. So it's 6.63 times 10 to the negative 34. You square it, and then 8 times the mass of electron, 9.11 times 10 to the negative 31, and then times the width, which is 250 PM, times 10 to the negative 12. You square it, and again you have a common factor. This is your common factor. So everything, so this multiplied by, in the bracket you have 2 squared and then minus 1 squared. Okay, so once you have that, then once you calculate the energy difference, which I don't have the number, but once you calculate this, your delta E, the change in energy has to be equal to the energy of the photon, which is hc over lambda. So whatever you calculate, you just set that lambda is equal to hc over your delta E. Okay, so again, your H here should be SI units, C is 3 times 10 to the 8th, and then delta E is whatever you calculated, and then what you're going to get is 6.88 times 10 to the negative 8. meters. So that's your part A. If you want to find the largest wavelength. Now, if you want to find the second largest, let's go back to this picture. If you want to go, so this is for part A, the changes from N to 1 to 2. Now, if you want to go up a little bit higher, the second longest wavelength will be when electron goes from n equal to 1 to n equal to 3. And likewise, you have n equal to 4. This is when the second largest, the third largest. So that'll be n equal to 1 to n equal to 4. Okay, so everything stays the same except that, for part A is n equal to 1 to n equal to 2. For part B, that's n equal to 1 to n equal to 3. For part C, that's n equal to 1 to n equal to 4. So without repetition, let me just write down the answers. So you have n equal to 1 changes to n equal to 3. And after you do the calculation, you'll find out the wavelength. The answer is 2.57 times 10 to the negative 8 meters. And for part C, your n equal to 1 jumping to n equal to 4. That's the third longest wavelength. So after you do the calculation, you will find that the answer is 1.37 times 10 to the negative 8 meters. Okay, so that's basically what you do. And the next one we want to do is, let's see, 16, problem 16. So for problem 16, we've done this we've done part A in class. So for part B, basically you ask to find, we have electron that's traveling in an infinite potential while you ask to find the probability of finding electron that is between, let's see, that is between 0.75 L to L. So let's say we do this, finding probability when the electron is confined with from 0.75 L to L. What is the probability of finding electron within this range? Okay, so so the wave function. So this is, let me see, problem 16. Again, the electron is in this ground state, so n equal to 1. So the wave function is, your n now is replaced by 1. So the wave function is a, and then times sine of, you have your n pi, so n equal to 1, so you have pi l over x. This is your wave function. Okay, your n here is 1 because it's in the ground state. And your a here is given, that's the amplitude, which is square root of L over 2. I'm sorry, 2 over L. Okay, so how do we find this? First of all, the probability of finding electron within that range is the wave function square dx. That's your starting point. And your x is from 0.75 L to L. Okay, and then, so you square this, so you have your a squared. So a squared, that'll be just 2 over L. So I put it outside the integral. And then you have your sine square. And then you have your pi L over x, and then dx. And your x range from 0.75 L to L. Now what we have here is that now you have some sort of form that's square, and you want to evaluate this. Like I said, what you need to do is do the change of variable. You defined your y to be in the argument of the sinusoidal function. So your y here will just be equal to pi L over x. Now, if you express your x in terms of y, then the range has to be changed as well. Okay, and also you have your dx that needs to be replaced by dy. So what is your dy? Your dy is equal to, am I doing, no, I'm sorry, pi over L. Sorry, this is pi over L and then x here. Sorry, that's around L, and this is x is in the numerator. All right, so sorry. So this is your L here. Your L should be in the denominator and x is in the numerator. So you have your dy, then that will be your pi, then you have your dx, and then over L. Okay, so your probability, so we copy it down, so your probability is now 2 over L, and then you have your sine square. Now within the argument, now you replace that by y. And your dx is actually L over pi, and then dy. Okay, and as I mentioned, when you change a variable, the range has to be changed as well. So when you have the, let's say the lower range, the lower limit is 0.75 L. So when you plug into this equation, well, your x is 0.75 L. So the your y now becomes 0.75 pi. And when you put the upper range to this equation, when x is equal to L, your y would just be pi. Okay, so now let's rearrange this. You have L that canceled, so now you have 2 over pi, and then you have your sine square, and then dy, and your y is ranging from 0.75 pi to pi. And so you are ready to evaluate. Like I said, this one is already given, so you do not have to, the sine square y dy, that is already been calculated, so you don't have to do the half angle. You just directly use the solution, and so you have so your p is equal to 2 over pi, and the evaluation of the integral is 1/2 y minus a quarter, and then sine 2y, and your y start from 0.75 pi to pi, and so you're ready to plug in the numbers. So you have your 2 over pi, and then your first term is 1/2 pi, and then minus 1/4 sine of 2 pi, this is the upper limit, and then minus in the parentheses, that's your lower limit. So we have 0.75 pi over 2, and then minus a quarter sine of, let's see, 0.75 times 2. 0.75 times 2, that will give you something pi, okay? And then the whole thing there. Okay, so this will be 1.5 pi. Sorry, let me just write it down here. So it's 1.5 pi, and so you can evaluate. So this one is just 1/2 pi. So this one gives you 0, and this one gives you something. And then after you do the calculations, plug in the numbers. This pi, that's in radians, so make sure that either you use change the mode on your calculator, or you just convert it to degrees and then calculate what the value should be for the sine of 1.5 pi. And then so the final answer, the answer would be, we're doing, where is we are doing part B. So part B, what you're going to get is let me see, part B. We're doing 0.75 to 0.75. Okay, so you're going to get these numbers, which is 0.091. Okay, so that's basically what the number is. Okay. And then we're going to do the last one, which is 33. So problem 33. So what are the energy and magnitude of the momentum and the wavelength of the photon emitted when the hydrogen atom undergoes a transition from a state with n equal to 3 to a state with n equal to 1? So in other words, now we're dealing with the hydrogens, and the initial state is at 3, which is the second excited state, goes down to the final state, which is ground state. You're asked to find the magnitude of, you're asked to find the momentum and the wavelength and also the energy of that photon when the hydrogen jump from n equal to 3 to n equal to 1. So this is energy level. This is n equal to 1, and this is n equal to 3, and the electron is jumping from n equal to 3 to n equal to 1. During that process, a photon is emitted. Okay, now the energy of an electron that's confined in the hydrogen atom is this. So your E is equal to negative 13.6 over n squared, and that's in EV. Okay, so now how do we find the change in energy? So the change in energy is equal to the energy of the electron, of the photon. So we need to find the change of energy. So delta E is equal to your E3 minus E1. So as I mentioned, the order of the subtraction will be that you are going to get a positive value because you're dealing with the change of energy. Okay, so so you have the negative 13.6, then you have your 3 squared, and then minus 13.6, and your n is 1, you square it. So this is the change of energy in EV, and you're going to get 12.08 EV. So that's part A, and you asked to find the momentum. How do we find the momentum of this photon when the photon has 12.08 EV? So here's what you want to do. Momentum of a photon is equal to the energy of the photon over speed of light. Everything has to be in SI unit. So you have your 12.08. You have to convert it to joules. And then divide it by the speed of light. So what you're going to get, so your P here, the momentum of the photon is equal to 6.44 times 10 to the negative 27th, and that's in kilograms times meter per second. Right, so once you have your momentum, you can calculate your energy of the the wavelength of a photon either by using this. Your lambda is h over p, or you can just use this equation that's lambda is equal to hc over delta E. Regardless, it has to be in SI unit. So I'm going to use the first one because I already calculated the momentum. So your H here is 6.63 times 10 to the negative 10 to the negative 34, and then divided by linear momentum you just calculated, which is 6.44 times 10 to the negative 27. So after you do this calculation, the wavelength is equal to 102.8 times 10 to the negative 9 meters. Okay, so that's the answer. Okay, so I'm going to stop the recording.